Hello, everyone. Thank you for joining my session at WACV 2026. Our goal is to boost classification accuracy in few-shot, fine-grained dataset. Unlike traditional methods that train classes independently, MBTI learns the relationships between similar classes. This allows our synthesized images to preserve the discriminative details. Few-shot, fine-grained classification requires precisely distinguishing between highly similar species or classes using only a very limited amount of training data. To achieve this, it is essential to capture fine-grained features, such as the specific patterns of a bird's feathers. Data augmentation is essential here because 1 to 8 shot constraints lead to a high risk of overfitting. Our synthesis must provide meaningful diversity while strictly maintaining class identity to reduce interclass confusion. One of the major challenges in personalization is the difficulty of capturing fine-grained, localized features. This issue becomes even more significant in few-shot learning settings, where data is extremely limited. To address this, we focus on representativeness. Existing research confirms that the quality of few-shot classification depends on how well synthesized images represent the true class distribution. A representative image must preserve essential details while ensuring diversity. Our MBTI achieves this by learning interclass relationships, ensuring every sample is both detailed and accurate for effective augmentation. Our method operates through a two-stage optimization process. First, the support embedding selection, or SES, identifies semantically similar neighbor classes in the text embedding space. Second, the distance metric module, or DMM, optimizes the embedding by learning discriminative features relative to these neighbors. This ensures our synthesized images are highly representative for fine-grained classification. The first stage is SES. To distinguish a target class from its visually similar neighbors, we must first identify those reference classes. As shown in the formula, we select the top K support embeddings based on cosine similarity in the text embedding space. These selected embeddings provide the necessary relational context for the model to learn the specific boundaries. The core of our method is DMM. DMM is a diffusion-based distance metric designed for text embeddings. As shown in the formula, we define loss dist. This term measures how much the predicted noise differs between the target and support embeddings. By minimizing this loss, the model learns the fine-grained discriminative features that separate the target class from its neighbors. Finally, this slide presents our overall objective function. The total loss MBTI, is composed of the standard latent diffusion loss, our proposed loss dist, and a regularization term. We optimize the ITA class embedding, WI star, by minimizing this combined loss function. This integrated approach ensures that the synthesized images preserve essential details while maintaining high representativeness for effective data augmentation. First, when combined with textual inversion, MBTI faithfully reproduces the intricate shapes and textures of a flower's center, which are often blurred by the baseline. This superior detail preservation extends to critical structures like aircraft engines and convertible roofs. Furthermore, as seen in the comparison with Sautier methods, integrating MBTI with LoRa or Dream Booth significantly enhances their output. For instance, while other models struggle with unique floral architectures or fine-grained wrinkled textures, our method successfully maintains these class-defining details. These results prove that MBTI consistently ensures representative synthesis across different generative backbones. Our MBTI achieved the best FID of 88.38, a significant improvement over baselines, while maintaining a competitive CLIP score of 0.341. Most importantly, as a plug-and-play module, MBTI consistently enhanced both LoRa and Dream Booth, proving its versatility and effectiveness in boosting generative models. As shown in the table, MBTI achieves the highest accuracy across nearly all scenarios. Notably, on the Flowers 102 dataset with 8 examples per class, we see a significant 10.5% performance gain over the second-best model. This consistent improvement across diverse datasets proves that our representative synthesis effectively overcomes data scarcity in fine-grained tasks. Our research addresses the critical challenge of interclass confusion in few-shot fine-grained scenarios by enabling representative data augmentation. We achieve this by learning the subtle differences between categories, allowing us to generate discriminative images that preserve essential class-defining details. As a result, MBTI achieved state-of-the-art performance in both classification accuracy and generative quality. Furthermore, as a plug-and-play module, our method demonstrates consistent performance improvements. This proves the robustness and practical versatility of our approach. Thank you for your attention.